Hello. Hello dear students, good evening everyone. So I hope all of you are on our channel 𝐂𝐤𝐬𝐞 English channel. I welcome you all of you. So let's start the today's session दोस्तों, and we'll be doing some good questions on machine learning for GATE 2026, and I expect that these questions might be some of the questions might come as your GATE 2026 paper. So let's start. So today we'll be doing machine learning questions for GATE 2026. Okay, so let's start the session. Okay, how many of you are actually prepared for GATE exam? How many of you are prepared for GATE exam दोस्तों? Okay, so let's start the session. Okay, so we have this question. This is question number 1. Okay, you are one nearest neighbor classifier. You are doing one nearest neighbor classifier with L2 distance. L2 distance means Euclidean distance. Okay, to classify the emails. Okay, the training set has n examples and the validation set has m examples. Okay, so we have n examples in the training set and validation set or the test set has m examples. Assume computing the L2 distance between the two emails takes a constant time. So what is the asymptotic time complexity of computing the validation error? So for each email in the validation, or we can say for each data point in the validation set, for each data point in the validation set, we need to find the distance from all the endpoints. We need to find the distance from all the endpoints. So we can say that for all m points in the validation set, we need to find the distance from all endpoints. Taken up for all endpoints. So how many distances we have to calculate? So we have to calculate total n into m number of distances. Here we have to calculate total n into m number of distances. Okay, so what is the time complexity? So we can say that the time complexity will be order of n into m, because it is given that the time complexity, or we can say that calculating the distance between the two emails takes a constant time. Okay, takes a constant time. Okay, so let's move on. आगे चलते हैं. Now, which of the following property is true about the original perceptron algorithm? So the perceptron algorithm, how many points are these correct? Let's see. The perceptron always converges to the best linear separator for a given data set. Is it fine? I don't think it's correct. The convergence criteria for perceptron depends on the initial value of the weight vectors. Obviously, yes, this is true. So initial value, initialization has the effect on the final result. This is true. Okay. Now the third one is, if the data set is not linearly separable, the perceptron does not converge and keeps cycling between some set of the weights. बिल्कुल सही है. This is also correct, because the perceptron or the single layer perceptron will work only when the data is linearly separable. So this is also correct. Okay, now if the data set is not linearly separable, the perceptron algorithm learns the linear separator with least misclassification. No, this is wrong. So B and C are correct. The single layer perceptron algorithm will work only when the data is linearly separable. And it will keep cycling when the data is non-linearly separable. Okay? Okay. Now, let's see the next question. I hope all of you are able to do it. You trained a classifier whose ROC curve is given. Okay. You would like to correctly classify the points that are in class, but you don't care what label you assign to the points that are out of class. In other words, your loss function is 1 when you predict z equals to -1 and the true label is y equal to 1. Otherwise, the loss is 0. Okay. The 4 red points below signify 4 classifiers. Of the 4 classifiers, which one has the lowest empirical risk on the test point? So first of all, we have to understand what is the loss for us. So the loss for us is, we'll read it again. You would like to correctly classify a point that is in class, but you don't care what label you assign to the points that are out of class. In other words, your loss function is 1 when your prediction is -1 and the true label is y equal to 1. Okay, so loss function is equal to 1 when class of the point is 1 but prediction is -1. Okay, but otherwise the loss function is 0. Means you are not worried about the negative class points, you are worried about the positive class points only. So we are worried about the positive class only. Okay, and not worried about the negative class. We don't worry about the negative class. So which one is best? A, B, C or D? So here we can see that in this case almost the true positive rate is equal to 1 and false positive rate is equal to, let's say, 0.5 or something at this point, C point. Okay, so true positive rate is actually true positive upon actual positive. Matlab all the actual positive are given positive. Okay, and we are not worried about anything else. Matlab we are not worried about the negative class points. Okay, so we are worried about the true positive class only. Means class 1 points should not be predicted as -1. This is important for us. So C is the best classifier for us in this situation. Is this fine to all of you? Please check and answer. Okay, now the next point. Consider single linkage and complete linkage hierarchical clustering. Is it possible for a point to be closer to the point in other cluster than to the point in its own cluster? If so, in which approach will this trend be observed? Means inside the cluster we have a point like this. So another is 0.6. Okay, so we have a clusters. So we have a condition that a point to be closer to the points in other cluster, means a point is closer to the points in other cluster than the points in its own cluster. Means we have elongated clusters. So in elongated clusters, what is the condition? So we have elongated clusters. In elongated clusters, what is the condition? In elongated clusters, means elongated clusters are created in single linkage only. Okay, in single linkage only. Okay, I think all of you are able to do it. Next. Suppose our input is two-dimensional sample point with 10 non-exclusive classes. Those points may belong to. Okay. So we have 10 classes. Okay. That is, a point can belong to more than one class. Suppose our input is two-dimensional sample point with 10 non-exclusive classes. Okay. Non-exclusive means a point can be can have more than one class. Okay, a point can have more than one class. Okay. Now, trainer classifier will build a fully connected neural network with bias terms that has a single hidden layer of 20 units and an output layer of 10 units. How many trainable parameters does this network have? It's a very simple thing. At the input layer, we have a data of 2 dimension. At the hidden layer, how many neurons are there? How many neurons are there? With 20 neurons. And at the output layer, how many neurons are there? 10. Okay. Now they are fully connected. Means how many connections will be there? There will be 40 connections. And here we will have 200 connections. We will have 20 extra bias and 10 extra bias. How many terms are there, dosto? So we can say that the total number of terms will be, or the total number of parameters will be 40 interconnections will be here, 200 will be here, 20 bias term and 10 bias term. So it is 200 plus 40 plus 20 plus 10. Okay, how many are there? So we can say it is 200 plus 40 plus 20 plus 10. So it is 270, I think, right? All of you are able to do it? Great. Next. Consider two support vector machine trained on the 2D feature space. The first SVM has a decision boundary. Okay, this is a decision boundary. While the second SVM has a decision boundary given by this. Which of the following statement is true? Okay. So we can see that the equation is 3x1 plus 4x2 plus 5 equals to 0. So this is the classifier of the case 1, right? This is the classifier of case 2. Now I think we have done this question in our 1500 series. I have done this question. Very beautiful question. The SVM with the bound. Now we have to compare the margins. We have to compare the margins. Now we know that the margin is 2 upon norm W. But we cannot tell the margin until and unless the marginal planes are given to us. Until and unless marginal planes are given to us, we cannot tell what is the margin of the SVM setup. Because it is very obvious that we cannot say that the margin is this. Margin is not equal to this. Until and unless the marginal plane are known to us. Because this classifier is same as multiplying this by 2. Okay, so this classifier will be same as this. Okay. So if we use W's of this, the margin will be different. If we use W's of this, the margin will be different. But the classifier will be same. So until and unless the marginal planes are known to us, we cannot say that the margin is equal to this. So we cannot compare the margins of the two classifier boundaries. Okay, we cannot compare the margins if the boundaries are known. Okay, the margins cannot be predicted with the given information, because until and unless the marginal planes are given to us, we cannot say, yeah, we cannot comment anything. We cannot comment anything on the margin. So D is the correct answer. Very beautiful question. I hope all of you are able to understand. Now we are doing binary classification on the class 1 and 2. We have a single data set of size n, of which a fraction of the elements are in class 1. To construct the test set, we randomly choose a fraction beta of the data set to put in the test set, keeping remaining elements in the training set. Okay. We would like to avoid the situation wherein training or the test set either class appears less than 0.1 n times. In which of the following situation does this occur in expectation? Okay, so we have to read it again. So we are doing binary classification on class 1 and 2. We have a single data set of size n. Of which a fraction alpha of, मेरे ख्याल से यहाँ पे alpha होगा, so of which a fraction alpha of the elements are in class 1. So we can say we have n number of points and alpha into n is in class 1 and 1 minus alpha into n is class 0 number of points. To construct a test set, we randomly choose a fraction beta of the data set to put in the test set. So, beta n into the test set. Okay. So, beta of the data set to put in the test set, keeping the remaining elements in the training set. Okay. So, this is the test set and obviously 1 minus beta into n will be in the training set. Now, we would like to avoid the situation wherein training or the test set either class appears less than, we would like to avoid the situation, this situation we want to avoid. Okay. Now, in which of the following situation does this occur in expectation? Okay. So, we want that in the training and the test set, and randomly they are chosen, right? So, alpha into n is the number of class 1 points and 1 minus alpha into n is the number of class 0 points. Out of these points, beta into n is taken as test set and 1 minus beta into n taken as a training set. Now, in the test set, okay, in the test set, we have beta into n, means out of this we take beta number of points or beta into n number of points. Okay, alpha n is the number of class 1 points and 1 minus alpha is the number of class 0 points. Beta is taken here. So we can say that in the test set, beta into alpha is class 1 number of points. Beta into alpha into n is number of class 1 points. Okay. Beta into 1 minus alpha into n is class 0 points. Okay, in the test set. Similarly, we go in the training set. So, in the training set, 1 minus beta into alpha n is class 1. And 1 minus beta into 1 minus alpha into n is class 0 points, right? Okay. Now let's move on. We have test and the training set. Now, we want that the number of points should not be less than 0.1 n times, means we can say that alpha into beta, beta into alpha should be greater than 0.1. beta into 1 minus alpha should be greater than 0.1. Okay, similarly 1 minus beta into alpha should be greater than 0.1. 1 minus beta into 1 minus alpha should be greater than 0.1. Okay, so these are the 4 conditions we need to check. Now, in which case this is following? Which of the following situation does this occur? So alpha 0.5 and 0.5. Is this valid? So we can check everything. 0.5 into 0.5 is greater than 0.1. Yes, obviously. So this is satisfied here in the option A. This is also satisfied. This is also satisfied. This is also satisfied. So if we take alpha beta 50-50%, all are satisfied. Okay. Now let's talk about this. Alpha is 40, beta is 60. Is this satisfied? Let's say 0.4 into 0.6 greater than 0.1. Perfect. Now I think this will also satisfy. Okay, because we can say the conditions will be 0.4 into 0.6, 0.6 into 0.4, 0.4 into 0.4 and 0.6 into 0.6. So these will be the conditions. I think all of will be getting satisfied here. What about this? Alpha is 20%, beta is 70%. So alpha into beta greater than 0.1, valid. Yeah, but this will fail in one situation because alpha is 0.2, 1 minus beta will be 0.3. So this will fail. This will fail. What about this 60 and 80%? So 0.3 into 0.6, this is valid, perfect. Next is if we do the subtraction 40% and 30% greater than, so obviously this will also be correct. So only C is the option where the condition will fail. Otherwise A is correct, B is correct and D is correct. In all the 3 the condition will follow. Okay, a very beautiful question, beautifully created and curated. All of you are able to do it, please check. Okay, so I hope all of you are able to do it. Let's move on to the next question. Now consider the training a decision tree with the design matrix of this and label is this. Okay, so perfect. Where F1 denotes the feature 1 corresponding to the first column of X and F2 is a feature 2. Okay, which of the following split the root node gives the highest information gain? So let's try to see. So we have the root node. Okay, so root node has all the data. Okay. Now if we bifurcate with this F1 greater than 2, F1 greater than 2, point number 1, 2, 3 and 4, only 4 points are there. Okay. So if we take F1 greater than 2, so F1 greater than 2 means first point, third point and fourth point are here. First, third and fourth means 1, 1, 0 classes and the only second point will go here, that is 0. So this is my option A. Let's see option B. F2 greater than 3. F2 greater than 3 means only one data point is here, first point, and this is our F2 less than equal to 3. F2 greater than 3. F2 greater than 3 means less than equal to 3 means first and second point will go here and third and fourth point will go here. So first and second means class 1 and 0. Here also class 1 and 0. So there is no need of entropy, is very poor here in this situation. Okay. Now let's see the third one. F1 greater than 4. F1 greater than 4. f1 less than equal to 4. So f1 greater than 4 means we'll take 6 and 9 means 1 and 3 here. Okay, so 1 and 3 means 1 and 1 class here, and obviously 0 and 0 class here. So we can see that the child are homogeneous in this case. Now the child are homogeneous means this is the best place in which the information gain will be maximum. Okay, I hope all of you are able to see this. So C is the correct answer, because we can see that in case of C, when the splitting is done as per the required condition, we are able to easily find out we have found out that the child or the children are homogeneous, and this is the condition that we need, right? I hope all of you are able to do it. Okay, so let's move on. Consider a binary classification one dimension data set with n examples which is linearly separable. Okay, a decision stump means a decision tree with only 2 leaves and depth 1 is used. Okay, the decision stump determines its threshold by finding the midpoint between the closest positive example and the closest negative example. Okay, if the data set contains at least 2 positive examples and 2 negative examples at least, what is the tightest upper bound on the leave one out error of the decision stump? Okay, so we have n examples. Okay, we have one dimension data set with n examples. That is linearly separable. A decision stump means we have a decision tree with depth 1, only 2 leaves are there, so means we have a root node. We make some decision, positive and negative. Okay, means only one dimension is there, so x is greater than something, x is less than equals to something. Okay, so we have the 2 terminal nodes are here. Now, the decision stump determines its threshold by finding the midpoint between the closest positive and the negative examples. If the data set contains n examples are there, at least 2 positive examples and 2 negative examples at least. What is the tightest upper bound? Means what can be the maximum upper bound on the leave one out error of the decision stump? Okay, we have n points. Okay, the data is there, n point data is there. So n point data is there. Minimum we have 2 positive and the 2 negative examples. So okay, so leave one out cross validation error we have to find out. Okay, if we take these as positive, these as negative, obviously the error will be 0. That's fine. We have to find out the upper bound, the maximum upper bound on this condition. The decision stump is there, the closest positive example and the closest negative example. Okay, so let's see doston. Yeah, got it. So in this case, suppose these are the positive points, these are the negative points. Okay, now the threshold condition will be, for example, we are doing the testing, so the threshold is found by positive and negative and the midpoint. Okay, So if this is in testing, obviously it will be correct. This is correct. This is correct. This is correct. This is correct. Now the question comes when this is in validation. If this is in validation, this is not in training. So the threshold will be found by this point, and obviously the threshold can be here depending on the values. The midpoint can be here also. The midpoint can be here also. So the point is, midpoint, if the midpoint is here, suppose this is in validation, this point goes in validation, this point goes in validation. So this is the point, the classifier point. So this is actually, we can say this is the point in validation. So the decision will be taken by this and this point. So this is the midpoint, let us say, between this point and this point. This is a threshold. So this will go in error. This may go in error, Similarly, suppose this is in validation. So the threshold will be found by the negative and the positive points, and obviously the threshold can be here. It can go threshold here. The threshold can be here. So this may go in error. This point may go in error. So obviously both these points have the condition that they may go in error. So out of n points, 2 points may go in error. This is the upper bound. Not more than 2 can be there. Maximum 2 errors can be there. So 2 upon n will be the answer. 2 divided by n. So what is the upper bound? Upper bound is 2 divided by n. Is it clear to all of you? Okay, I hope all of you are able to do it. Okay, is this fine? I hope all of you are able to do it. Let's try to move on. Okay, we have a function which takes two-dimensional data x1, x2 and has parameters w1, w2 given by this. What is this? I think there is some typo error here. There is some typo error. Okay, we use the back propagation to estimate the right parameter value. We start by setting both the parameters to 0. Assume that we are training a point x1, x2 and y equals to 5. Given this information, answer the next two questions. What is the value of del f upon del w2? वो फाइंड तो हो जाता, बट मेरे ख्याल से देयर इज अ टाइपो एरर, तो वी कैन इजीली फाइंड आउट द डेरिवेटिव, बट देयर इज अ टाइपो एरर, सो वी आर स्किपिंग दिस. Okay, now let's try to see this. The SVM. Okay, now consider the set of the labeled example. This is the labeled example which is given to us. Okay, the soft margin SVM formulation is given as, the soft margin SVM is given to us. We know what is the formulation. Okay, subject to the condition. Okay, we know what is the condition. Which of the following statement is true about the support vectors? Now, yesterday itself, दोस्तों, in Maha revision session, we have seen that the support vectors are the points where lambda is non-zero. Now, lambda is non-zero means for all the points where epsilon is greater than 0, obviously these are the points where we have support vectors. ठीक है ना? Okay. Now, for some support vectors, epsilon is equals to 0, and for others, epsilon is greater than 0, right? Is the correct answer? We know that the support vectors which are at the marginal plane, they have epsilon equal to 0, error equal to 0, or the slack variable is 0. But for the points which are inside the marginal plane or between the marginal plane, or they are misclassified, here we have epsilon greater than 0, right? So C is the correct answer. I hope all of you are able to do it. Okay, now let's see. We trained a multi-class logistic regression model with the following weights. Weight matrix. So this is the weight matrix that is given to us. Okay. Theta A, theta B and theta C are the weight vectors for class A, B and C. Okay. Respectively. Let the data point as this. The data point is this, determine the class label. So it is very easy for all of us. So we'll find out theta A. Okay, we'll use the variables, the weights of the classes A, B and C. We'll multiply point A by theta A, multiply point A by theta B, multiply point A by theta C. Okay, so we can see that theta is this, A is this, theta A, theta B and theta C is this. So A is 1 minus 1 and 1. Theta A is 1 0 0, so the value is 1. Theta B is 0 1 0, the value is minus 1. Theta C is 0 1 1. So A multiplied by this 0 1 1 will be 0. So we can say that A into theta A is maximum 1. This is minus 1 and this is 0. So we can say that A multiplied by theta A is maximum. So the points belong to class A. The points belong to class A. I hope all of you are able to do it. Just check दोस्तों, all of you are able to do it or not. Okay, I hope all of you are able to do it. Now let's move on to the next. Which of the following is not a convex function? Okay, so linear function is not a convex. Square is a convex function. ReLU is a convex function. Sigmoid is a convex function. Obviously not. Okay, this is also not a convex function. So obviously A, B and D are not convex. A, B and D. Only C is a convex function, right? I hope all of you are able to do this simple mathematical problem. Okay, next. Okay, suppose you train a polynomial regression. Obviously this is not in syllabus, so we'll skip the question. Polynomial regression is not in syllabus, we'll skip it. Which of the following is true about the optimum learning rate? Optimum learning rate means related to gradient descent. Please try to do it. So for the convex loss function, the batch gradient descent is guaranteed to eventually converge to the global optima, while stochastic gradient descent is not. For convex loss function, the stochastic gradient descent is guaranteed to eventually converge to the global optima, while batch gradient descent does not. Okay, so just try to do this question. Okay. So I think all of you are able to do this. And if we have a convex function, then obviously we'll reach the global optima. So both will help us, both stochastic as well as the batch gradient descent will eventually lead the global optimum. Okay, both will give us the solution. Okay, I hope all of you are able to do it. Next, LS has collected a data set of dependent and independent variables, okay, x1, x2 and this thing, and perform linear regression on it, obtain the weights vector, okay, WLS. Bob collected the same data set but recorded each feature in different units. Okay, if each feature with different units. Okay, I hope all of you are able to see this. So for example, we have A, B and C. The values are P, Q and R. Here he has calculated 2 times of these and 3 times of this. Which of the following statement is correct? Now this is a very beautiful question. You can try this and it's a very simple understanding based question. So they have the same training loss but W's are equal. They have different training loss, W's are equal. They have same training loss, W's are not equal. They have different training loss, W's are equal. So please tell me what is the answer. Try to do this question, दोस्तों. Okay, so here we can see that दोस्तों, only we have doubled the dimension values and tripled these dimension values. So obviously if the weight is W of this and the weight of this is, let's say, Z, so obviously the weight here will be W upon 2 and Z upon 3, right? Because the dimensions are doubled and tripled, so this has to be the case. Okay, so obviously the dimensions cannot be equal in both the case, but the error will be same. So both will have same training error, but W's will not be equal. Okay, W's will not be equal. C is the correct answer. I hope all of you are able to do this. Okay, now let's see a question. A company named Amazing this thing, okay, using k-means clustering to determine the optimal location for their K stores in the given region, has 4 customers in mega city located at the point X. Okay, the plan to build 2 stores with initial guesses for the store location represented by the triangle. Okay, using the FC mean loss function. Okay, what is the final loss function after the k-mean algorithm converges and the store are optimally placed? Okay, It is using k-mean clustering to determine the optimal location for their k stores, okay, in the given region. Has 4 customers in this, okay. They want to build 2 stores, okay, they want to build 2 stores. They plan to build 2 stores with initial guesses for the store located represented by this in the plot. I think only one plot is there. Only one triangle is there. So let's say both the stores are here initially. But this cannot be the case, right? It has to be points. Let's say the second triangle is here. Okay. These are the customers. Okay. So this is a loss function. We want to minimize the distance between the point and the mean location of the cluster ka square. So what will be the answer? Please tell me. Try to solve this question, दोस्तों. Okay, so let's try to solve this question, दोस्तों. So the point is, we have to find out the 2 clusters here, and the mean location will be the location of the store. Okay. Okay. So obviously, if we start doing the k-means clustering, obviously this center will become the cluster, and this will become the cluster like this, because if the starting cluster point is this and this, so these 2 points will go into this cluster, obviously this. So we can see that these 2 points will go into one cluster, these 2 points will go into other cluster, and obviously the mean location, this will be the store location, and this will be the store location for these points. Okay. Now we have to find out the loss function. Loss function is the distance of the point from the mean location. Okay. So we can see that ka square. We can see that here the point is 1, 1, 1 and 1. So the loss value will be 4 finally. And we'll have stores at this location and at this location. Okay. This was a very beautiful question. You must have tried this. Now, this is also a very beautiful question. Okay. Consider the soft margin SVM to the training data, here each with a different value of the hyperparameter C, the penalty parameter. Now, we have to run, we first run with C equals to CA, then second C equals to CB, then C equals to CC. Which of the following option correctly orders CA, CB and CC? Like for A, we get this as a boundary. For B, we get this as a boundary. For C, we get this as a boundary. So, how can you compare CA, CB and CC? Just try to do this question. Okay, so let's try to see दोस्तों. We can see that if we increase the value of C, for example, if C is equals to 0, we get the result same as a hard margin SVM. Okay, now if C is large, then obviously we can, if C is large, then obviously if C is large, then it becomes a hard margin SVM, because then we want epsilons to be 0. If C is small, then epsilons can be large. Okay, so here we can see that if we take this as a classifier, A, so this will be the marginal plane and this will be the marginal plane, obviously, in that case. Okay, if B is a classifier, then this will be the marginal plane and this will be the marginal plane, obviously. This is the margin for A, this is the margin for B, and if C this is, then this will be the margin for C. So here we can see that for C case we have a very large margin, but we have more errors. So CC will be very small, CB will be large and CA will be largest, because for CA this is same as the hard margin SVM. Okay, I hope all of you are able to do it. It's a very beautiful question. So CC, CB and CA, this is the correct answer. Okay, now let's see one more question. Which of the following statement about the gradient descent are true? After a gradient descent update step, the objective function value at the weight vector is always lower after the update than before. Okay, there is always a unique steepest descent direction in the gradient descent. Gradient descent converges to the global optimum minimum for the logistic regression under the appropriate assumption. Since ReLU is a convex function, the neural network that uses ReLU activation is also a convex function, and therefore the gradient descent will converge to global optimum solution on the neural network with ReLU activation function. What are the answers is correct? Which of the following statements about this are true? So obviously, after a gradient descent update step, the objective function value at the weight is always lower. No, because depends on the learning rate. If the learning rate is such that we are actually jumping the solution, we are moving to other side, then it may increase also. There is always a unique steepest direction in gradient descent. This can be a correct answer. Now, gradient descent converges to global minima for logistic regression under the appropriate assumption. Logistic regression, we don't apply actually the gradient descent. ReLU is a convex function. The neural networks that use ReLU activation function. So, what do you think, dosto? ReLU is a convex function. Okay, so yes, ReLU is a convex function. Yes, ReLU is a convex function, and obviously this is also correct. Okay, I hope all of you are able to do it. Okay. Okay, so let's do this one also. Suppose we have a data set, we divide into 3 equal sizes A, B and C. We fit 3 linear regression model with L2 regularization X, Y and Z on all A. Okay. Each model uses the same feature in the training set. The only difference is lambda used by each model. Select the below. Suppose Z has the lowest average loss on B, and model Z will have the lowest average loss when evaluated on C. If A and B have the same exact mean and the variance, the average loss of the model Y on B will be exactly equal to the average loss of Y on A. If lambda is 0 for model X, the loss of XA, loss of YA and loss of XA will be less than. Okay. If lambda Y is less than lambda Z, then loss of YA will be less than loss of ZA. So let's try to read this one time. Suppose we have a data set with divided into 3 parts A, B and C. We fit 3 linear regression model with L2 regularization, that is ridge. Okay. Okay. Each model uses the same feature and the training set. The only difference is lambda. So we have lambda X, lambda Y and lambda Z, and model are trained on A. Models are trained on A dataset only. Now, if lambda Y is less than lambda Z, then loss of Y on A will be less than loss of Z on A. So obviously, dosto, if lambda is less, so it is same as linear regression. So if lambda is less than this, so it is more as a linear regression. Okay, but we cannot actually say this because it depends on the situation also. Okay, we can have lambda very large value, so this is less than this value, so we cannot comment on this. If lambda is 0 for model X, okay, if lambda is 0 for model X, then this will be less than this. So आप देखोगे yes, because this will become linear regression, this will become ridge regression. So this is overfitting model and this is normal ridge regression model, and obviously loss of X will be less than loss of ZA. This one is correct. I think C is the correct answer. If A and B have the same exact mean and variance with data distribution, the average loss of model Y on B will be exactly equal to average loss of Y on A. No, because Y is trained on A, right? So on B it may have different errors. Suppose Z has the lowest average loss on B, model Z will have average loss when evaluated on C. No, not necessary. Not necessary. Only C is the correct answer. Okay. So I think we have done a lot of questions. Thank you.